Today we're going to talk about one of the most important and most commonly replaced components in vintage radio restoration, the capacitor. Hi everyone, I'm Jim Hounshell and welcome to the Old Radio Revival. Today we're going to dig into one of the most essential components in any antique radio, the capacitor. We'll talk about what they are, how they work, the different types, and why they're so important for restoring antique radios. Now, a capacitor may not look like much at first glance. It's often just a small cylinder or block tucked under the chassis, but its job is critical. Capacitors store energy and release it at just the right time, filtering out unwanted hum, smoothing voltage, or helping a circuit resonate at the correct frequency. Without capacitors doing their job, your radio may buzz, hum, or fail to play altogether. That reminds me of something that Jesus said in Matthew 12:34. For out of the abundance of the heart, the mouth speaks. Just like a capacitor stores up energy and then releases it, our hearts store up what we dwell on, and eventually that comes out in our words and actions. If we're filling our hearts with anger, pride, or sin, that's what will spill out. But if we're filling them with God's truth and love, that will overflow into our lives. The Apostle Paul also gives us this encouragement in Philippians 4:8. Finally, brothers, whatever is true, whatever is honorable, whatever is just, whatever is pure, whatever is lovely, whatever is commendable, if there is any excellence, if there is anything worthy of praise, think about these things. You see, capacitors in a radio have to be the right kind, with the right values, and in good condition, or else the whole system suffers. In the same way, what we allow into our hearts and minds matters. If we store up the wrong things, our lives will buzz with static. But if we let God's Word fill us, our lives become clear channels of His truth and grace. So as we explore capacitors today, I want you to remember, just as a good capacitor stores and releases energy at the right time, so a heart filled with God's Word will overflow with His goodness at just the right time. Now let's take a look at capacitors. Let me start with the basics. A capacitor is a device that stores electrical energy in an electric field. Think of it like a tiny rechargeable battery, except it charges and discharges almost instantly. The basic construction is simple. Two conductive plates separated by an insulating material called a dielectric. When you apply voltage across those plates, electrons build up on one plate and are depleted from the other. This creates an electric field between the plates, and that field stores energy. The amount of energy a capacitor can store depends on three things: the area of the plate, how close they are together, and what type of dielectric material is between them. Capacitors perform a variety of essential jobs in vintage radios. Understanding these functions is key to proper restoration. One major function of a capacitor is to store energy and use it for filtering. In the power supply section, large electrolytic capacitors store energy and smooth out the pulsating DC from the rectifier tubes. Here's how it works. When the rectifier tube conducts, it produces pulsating DC. The voltage rises and falls 60 or 120 times per second. Without filtering, this would cause a loud hum in the radio. The filter capacitor charges when the voltage is high and discharges when the voltage drops, filling in the gaps. This smooths the DC into a steady voltage. The larger the capacitance, the more energy it can store and the smoother the DC becomes. That's why power supply filter capacitors are typically large, ranging from 10 to 80 microfarads. Another key job is coupling. A coupling capacitor links one stage of a circuit to the next by allowing AC signals to pass while blocking DC voltages. This lets the desired signal move between tube stages that may have different DC voltage levels, without transferring the DC itself. The value of coupling capacitors is chosen based on the frequencies you want to pass. For audio coupling, you typically see 0.01 to 0.5 microfarads. For RF coupling, the values are much smaller, usually 50 to 500 picofarads. Capacitors are also used for bypassing and decoupling. Bypass capacitors provide a low impedance path for AC signals to ground, while allowing DC to continue through the circuit normally. This prevents unwanted feedback and instability. Typical values range from 0.01 microfarads for audio bypassing and up to 0.1 microfarads for RF bypassing. Some capacitors work with resistors to shape the frequency response of the radio. They create filters that emphasize or de-emphasize certain frequencies, which can make the audio sound more bass-heavy or treble-heavy. In a variable tone control, a potentiometer is wired in series with a capacitor. The pot lets you control how much of the high-frequency signal is bled to ground. With the pot at maximum resistance, the circuit has little effect. As you decrease resistance, more high frequencies are sent to ground, reducing the treble. Finally, capacitors are essential for tuning. Variable capacitors work with inductors to create tuned circuits that select specific radio frequencies. As you turn the tuning dial, you change the capacitance, which changes the resonant frequency of the circuit and lets you select the station you want to hear. So as you can see, capacitors aren't just small components. They're critical for filtering, coupling, tone shaping, and tuning in every vintage radio. We've looked at how capacitors are used in different applications. Now, let's look at the various types you'll encounter in antique radios. The most common are paper capacitors, electrolytic capacitors, mica capacitors, and variable capacitors. Let's go through each. Paper capacitors are the ones you'll see most often in vintage radios. They came in tubular and rectangular shapes. Tubular capacitors were the most common in early tube radios. They were constructed from layers of metal foil and oil or wax impregnated paper. They were sealed in a brown paper tube with wax or pitch plugs to prevent moisture absorption. They almost always had axial leads with wires extending from each end. They were used for coupling, blocking, filtering, and bypassing, with typical values from 0.001 up to 1 or 2 microfarads. Values were either printed on the tube or indicated with colored stripes, using a color code to show capacitance, tolerance, and voltage. Rectangular paper capacitors served the same purpose and used a series of colored dots or bands to indicate capacitance, tolerance, and working voltage. Interpreting these required an EIA color code chart. The problem with paper capacitors is that paper is an organic material. It degrades over time. After 70 to 80 years, moisture absorption causes the paper to break down. The capacitor may leak current or it may short circuit. Some show no outward signs of failure, while others may have swollen or cracked cases, wax leakage, or discolored wrapping. Here's a rule of thumb. Replace every paper capacitor, even if it tests good. Modern film capacitors, polyester, polypropylene, or metallized film, are reliable replacements. Polyester film capacitors are general purpose, stable, and available in most values you'll need. Polypropylene film capacitors have low distortion and good stability for audio applications. Metallized film capacitors are self-healing and good for high reliability uses. Always use the same or higher voltage rating than the original and match the capacitance as closely as possible. These replacements are non-polarized, so polarity doesn't matter. Electrolytics are the large value capacitors used for power supply filtering. They consist of aluminum foil plates and an electrolyte forming the dielectric. On top of the chassis, they are usually in tall metal cans. Under the chassis, they may be mounted in a metal clamp. Electrolytics are polarized with clear positive and negative terminals. Connect them backwards and they can explode. The positive connects to the higher voltage, the negative to ground or a lower voltage. Old electrolytics usually have capacitance and voltage clearly marked. For example, a 20 to 40 MFD with 450 volts for dual section units. Electrolytics have a limited lifespan. Over decades, the electrolyte dries out, capacitance drops, and equivalent series resistance increases. Always replace them. Modern replacements are standard aluminum electrolytics, or for specialty needs, long life or low ESR types for better filtering and durability. Dual or triple section electrolytics can be replaced with individual capacitors, or you can gut the original can and install modern capacitors inside to maintain the original appearance. Mica capacitors are used in RF circuits where stability and low loss are important. They use thin sheets of mica as the dielectric and are usually small, rectangular, and marked with colored dots. Values are typically 10 picofarads up to 0.01 microfarads. Mica capacitors often survive decades without degradation, so if they test good, they can usually be left in the circuit. Then there are variable capacitors. The tuning capacitor has moving plates that mesh together as you turn the shaft. One set is fixed, the stator. The other moves, rotor. Capacitance changes as the plate overlap changes. Maximum capacitance occurs when plates are fully meshed. Most radios use ganged capacitors, where 2 or 3 sections are mounted on a single shaft. There's the RF section that tunes the antenna and RF amplifier circuits, the oscillator section that tunes the local oscillator circuit, and sometimes a third section for additional RF stages or band switching. All sections must track together for proper tuning and stable IF frequency. The frame holding these sections is usually heavy aluminum or steel for stability. Tuning capacitors rarely fail electrically, but may develop mechanical problems. Bent plates, causing shorts, dirty plates, worn bearings, or misalignment. Minor issues can often be corrected by straightening plates carefully, cleaning with alcohol or deoxit, lubricating the shaft, and including alignment in your restoration process. Trimmer capacitors are small variable capacitors used for precise adjustment during alignment. They usually have 2 small metal plates with mica or ceramic dielectric in between and have a screw adjustment. As you turn the screw, one plate moves closer or further from the other, changing the capacitance. The capacitance typically ranges from 3 to 30 picofarads. They can be found in the antenna circuits where they're used to peak antenna coupling for maximum signal transfer, or in the oscillator circuits where they fine-tune the local oscillator frequency for proper tracking. On IF transformers, they adjust the resonant frequency of IF stages for optimal selectivity. In the RF stages, they peak RF amplifier stages for maximum gain. There are some common problems with trimmer capacitors. For example, the adjustment screws can work loose over decades, causing frequent drift. Dust or oxidation on the plates causes poor contact and instability. The adjustment mechanism can wear out, making fine adjustment impossible. And the mica or ceramic can crack, causing erratic capacitance changes. You can test trimmers with a capacitance meter, but you'll need to disconnect at least one end from the circuit. Check that the capacitance changes smoothly as you adjust the screw. Erratic readings indicate problems. Modern trimmer capacitors are available and you can find direct replacements. Make sure to get the same capacitance range and physical size. You should be aware of the significant safety risks when working with capacitors in vintage radios. For example, filter capacitors in tube radios can hold dangerous charges even when the radio is unplugged. Always discharge these capacitors before working on the radio. Use a bleeder resistor or a capacitor discharge tool to safely and quickly remove stored electrical energy from a capacitor before maintenance or repair work. This will remove the potential for an electric shock to you and damage to the equipment. Large capacitors can hold a charge for hours or even days after the radio is turned off. Also, in some radios, some capacitors connect directly to the power line. These are line filter capacitors used to suppress radio frequency interference, either from coming into the radio from the power lines or leaving the radio and affecting other devices. Original paper or molded paper capacitors are prone to failure and can be hazardous. For safety, replace them with modern, safety-rated capacitors, typically X1, Y2 types. These capacitors are designed to fail open rather than short, helping prevent dangerous situations. Always use proper safety capacitors for line-connected applications. Still another risk has to do with electrolytic capacitors. If connected with reverse polarity, in other words, if you connect the positive side of the capacitor to the negative terminal, they can explode. The same will happen if they're exposed to excessive voltage. Always double check polarity and be sure you're using the right size capacitor before applying power. If you're not sure, use a variac to bring the voltage up slowly while monitoring the capacitor. Finally, bad capacitors can overheat and potentially start fires. Don't leave a radio unattended during initial testing after restoration. If you smell burning or see smoke, turn off the radio immediately and investigate. Now let me share some common mistakes that beginners often make when replacing capacitors. First, never use a capacitor with a voltage rating lower than the original. The voltage rating must be at least as high as the highest voltage the capacitor will see in the circuit. When in doubt, go higher. For example, a 600 volt capacitor will work perfectly fine in a 400 volt application. Another common mistake is connecting electrolytic capacitors backwards. As we mentioned earlier, always double check polarity before applying power. A third mistake is using ceramic capacitors in audio coupling applications. Ceramics can introduce distortion. For the best results, match the capacitor type to the application. Also, never use acid core solder. It will corrode your connections over time. Use rosin core solder instead, and be careful not to overheat components while soldering. Poor mechanical mounting or loose connections can cause future problems. Finally, when replacing filter capacitors, replace all of them, not just the ones that look bad. Mixing old and new capacitors in the same circuit can cause uneven current sharing and premature failure. Avoiding these mistakes will help ensure your restoration is safe, reliable, and long-lasting. Understanding capacitors is absolutely essential for successful vintage radio restoration. They're probably the most commonly replaced components, and they're involved in almost every aspect of radio operation. Remember the key points. Always replace paper and electrolytic capacitors. Use proper voltage ratings and capacitor types. Pay attention to polarity, and use good installation practices. The time you spend understanding and properly replacing capacitors will pay off in decades of reliable operation from your restored radio. For a detailed look at another important component in radio restoration, check out my video Understanding Resistors in Vintage Radios, also part of the Beginner series. If you found this video helpful, give it a thumbs up and please subscribe. Thanks for watching the Old Radio Revival, and I'll see you in the next one.